Hello everyone, I'm Suraj Kothari. It may not be intuitive, but I'm going to talk about algebra as a fundamental technique to reason about safety, security, and correctness of software. What does algebra have to do with software? In school, we learn to set up equations and solve word problems using algebra. We shall see that the same algebra can help to solve complex software problems. It will be amazing to see that zillions of software execution behaviors can be easily represented and analyzed using algebra. The algebra gives us deep insight into software. It shows that the complexity of execution behaviors is not different for structured versus unstructured programs. Moreover, unstructured version could be more desirable because it avoids code duplication. Discovery consists of looking at the same thing as everyone else and thinking something different. Experts have contemplated techniques such as the binary decision diagram to manage exponentiality of software behaviors. We will think differently using techniques akin to high school algebra. Years later, you may remember these as lectures on how difficult but worthwhile it is to make things simple. More than a technical presentation, this will be an exploration to discover mathematical magic that can help us understand and manage complexity of software. Software execution creates sequences from a set. An execution behavior is a sequence of executed program statements during a program run. Software safety and security is of critical importance. Recognizing societal and national importance of software security, DARPA has launched several programs to advance analysis and verification of software systems. Software analysis techniques can be put in two buckets: techniques that analyze software by running the program, techniques that analyze software without running the program. In either case, the fundamental challenge is the number of execution behaviors is exponentially large even for small programs without loops. With loops, the number is as good as infinite. We employ a practical notion of correctness. A verification function can return true for correct and false for incorrect for each execution behavior. The verification functions are based on their applicability to software safety and security challenges. A program is correct if and only if the verification function returns true for all execution behaviors. We shall illustrate how algebra handles exponentiality challenge. We'll use small examples first. This is a simple example without loops. On line 17, we have x divided by d. If d is equal to 0, we have a division by 0 vulnerability. This program will have many execution behaviors because of the conditions at line 5, 8 and 9. We will assume that the inputs a1 and a2 can take values between 1 to 2 to the power 32. Even for this small program, About 1 trillion test runs are needed to detect the DBZ vulnerability with high probability. The challenge is to test as little as possible, test less, but test smarter. The execution behaviors can be represented by a truth table. We have 3 conditions, so we will have 8 rows in the truth table for different combinations. Each row of the truth table represents one execution behavior. For example, the first row is when the 3 conditions are all true. The execution behavior is program statement 3, 4. If 5 is true, then 6, then 8 is true, then 9, 9 is true, then 10, 17. We will use a dummy B for beginning and E for end. The 8 rows of the truth table have 6 distinct execution behaviors, of which 2 have DBZ vulnerability. So the fraction of vulnerable behaviors is 1/3. Can we compute the fraction without enumerating the behaviors? Binary decision diagram is a technique for compact representation. The execution behaviors can be represented using a decision diagram. Here we have shown the representation of execution behaviors for the DBZ program using a decision diagram. The dotted line in a decision diagram corresponds to the condition being false, and the solid line corresponds to the condition being true. So for example, if C1 is false, C2 is true, and C3 is true, we get the behavior 3. You can see the correspondence between the behaviors represented through the truth table and the decision diagram. The compactness achieved by a decision diagram depends on the ordering of the conditions. In this example, if we choose the ordering C3, C1, C2, then you can see that the decision diagram is not compact. It has the same replication of behaviors as in the truth table. This second example introduces the complexity of loop behaviors. Here we want to check that lock is always followed by unlock during every execution behavior. The representation of loop behaviors becomes an issue with truth tables and decision diagrams. This example is about an unstructured program. The control flow for the unstructured program is shown here. We want to check if L is followed by U. This example, in addition to the complexity of loop behaviors, also has the complexity of unstructured-ness. Now let's summarize the 3 examples. The first example, the verification function will return true if the execution behavior does not have a division by 0. And in that example, we want to check that the verification function returns true for every execution behavior. For the second example, the verification function returns true if lock is followed by unlock. In this third example, the verification function returns true if L is followed by U. As I was working on the algebra to manage complexity of software execution behaviors, I was reminded of this quote by Steve Jobs. Simple can be harder than complex. You have to work hard to get your thinking clean to make it simple. But it is worth it in the end because once you get there, you can move mountains. Our effort is to make software analysis and verification simple, and to do so, we invoke the magic of mathematics. The famous physicist Edward Teller says science attempts to find logic and simplicity in nature. Mathematics attempts to establish order and simplicity in human thought.